Deep inside a power plant, there's a machine, weighs tons, and it's spinning with this almost unbelievable steadiness. Now, its speed isn't just fast, it's locked perfectly and mathematically to the entire electrical grid. So what do you think happens when you try to push it even harder?
Well, when operators crank open the valves and just flood the turbine with more steam, you naturally think the whole thing would speed up, right? I mean, that's what a giant burst of energy should do. But it doesn't. The speed stays almost perfectly constant. And yet, somehow, the generator starts pumping more power out to the grid. So, how is that even possible?
Seriously, how can a machine just absorb more and more energy without actually accelerating? What invisible force is holding this spinning giant in place, letting it turn all that extra push into pure electricity?
Well, the secret isn't mechanical at all. There's no giant brake or some kind of clutch system. It's something you can't see. It's an invisible but incredibly powerful connection, a magnetic link between that spinning machine and the entire electrical grid.
I want you to just imagine two unbelievably powerful magnetic fields, and they're interacting with each other without ever physically touching. The forces we're talking about here are just immense, and this magnetic dance, well, that's the key to the whole thing.
And here they are, the two main players in this, let's call it a magnetic tug-of-war. On one side, you have the magnetic field from the spinning rotor. That's the heart of the machine itself. And on the other, you've got a rotating magnetic field in the stationary part, the stator, which is actually created by the grid it's connected to.
Now, these two fields are so incredibly strong that they literally lock onto each other. They spin together in perfect synchronism. At this point, the rotor isn't a free agent anymore. It's electromagnetically chained to the grid, forced to spin at the exact same frequency.
So if they're locked together so tightly, how in the world does more power get transferred? This is where we get to the idea of a stretch in that magnetic bond.
This stretch has a name. It's called the load angle. And it's just the angular difference between the rotor's magnetic field and the stator's. You know, when there's no load, no work being done, they're perfectly aligned. But as soon as the generator has to start working, that all changes. The best way to picture this is like an invisible magnetic rubber band that's connecting the rotor to the grid. As the turbine pushes harder and harder, that band starts to stretch. That stretch, that invisible angle, that is the load angle.
Okay, so now let's look at how this tension, this actual stretching in the magnetic bond, is what pushes power out into the world.
All right, so here's exactly what happens, step by step. First, more steam creates more torque, which tries to make the rotor speed up. As it pushes forward, it advances its field, which increases the load angle, stretching that magnetic rubber band. And it's the tension from that stretch that actually transfers the power over to the grid.
And the relationship here is just beautifully simple. The more you stretch that magnetic bond, the bigger the load angle gets, the more power flows from that generator into the system. The speed stays locked, but the angle and the power output, they rise together.
But of course, that magnetic bond can't just stretch forever. If you push the turbine too hard, it can snap. And this is where things can get really dangerous.
The breaking point, the absolute limit, is a load angle of 90 degrees. This is called the stability limit. At this exact point, the generator is putting out its absolute maximum power. Push it any further, and the whole system can become violently unstable.
And here's the crucial part. Once you go past 90 degrees, that magnetic force that's holding the rotor in sync actually starts to get weaker. So with less resistance holding it back, all that massive energy from the turbine causes the rotor to accelerate like crazy, breaking free from the grid.
When a generator slips a pole like this, the results are, well, they're not pretty. The machine gets hit with these violent mechanical stresses. As one of our sources puts it, these torque pulsations will cause damage, possibly catastrophic damage to the machine.
So this isn't just a story about one machine. This is about the stability of our entire electrical world.
You see, the entire power grid is really a massive network of all these synchronized generators, and each one is acting like an anchor holding the whole system together. The load angle then becomes this hidden signal that tells us just how hard each of those anchors is being pulled on.
So, to bring it all back together, when a generator has to deliver more power, it doesn't just spin faster. Instead, it leans farther into its magnetic bond with the grid, stretching that connection to push more energy through.
It's a machine of pure steel, held by a bond of pure magnetism. The load angle, it's the invisible anchor that holds our entire electrical world together, perfectly and beautifully.
in sync.